So we will start our first presentation for the class ME 407, which is robotics detail, prelude, sorry. This is the first team. This year project is actually a two-team project where two teams are going to build two different elements of the same system that is going to be assembled later on at the end of the spring semester. And so our first team is the Scorpius team, and I'll let them start. Thank you for the whole panel group to come, and I hope you will enjoy our presentation. Thank you.
Thank you for that introduction, Dr. Gentilini. We are Scorpius Robotics, and this is our preliminary design. My name is Austin Wild, and I'm the design team lead for this team.
My name is Hillary Nelson. I'm the mechanical team lead.
I'm Andrew Dietrich. I'm the software team lead.
I'm Jennifer Stiles, and I'm on the mechanical sub-team.
I'm Nick Harris. I'm also on the mechanical sub-team.
I'm Robert Noble, and I'm on the electrical sub-team.
A brief overview of what we're going to be talking about today. We will start with our objectives, move on to our requirements ranking, our preliminary design results. We will then talk about our various subsystems, our budget, our feature timeline, and then we will conclude. So the objective of our team is that we will design and build a robotic arm that will act as a tail for the hexaplot body. The hexaplot body is being designed by the other ME robotics team. The primary objective of our arm is, or tail, as it will henceforth be referred to, is that it will be able to identify and share information about fires. The secondary objective is that it shall have an end effector or a draw. And our tertiary objective is that it shall be able to draw a picture for competition in the 2017 RoboGames Challenge. I will now speak about our requirements ranking. This is the way in which we ranked all of our requirements. On the horizontal and vertical axes, we have our systems, and those are all the same systems on the horizontal and vertical. What all these numbers mean is whenever you see a 1, that means that the system in the horizontal is more important than the system in the vertical. And therefore, our actuation system is more important than our manipulation system if you look in the top left corner. After we ranked all of our systems, we added them up across the horizontal to get our total weight. And we determined that power and processor are our most important systems with a total weight of 13. I'll now speak about our preliminary design results. This is our first preliminary design, our preliminary design A. For each of our systems, we came up with 3 different design options and chose the best path based off the decision matrix. Highlighted in dark gray is the path we have chosen for design A, and we determined these components or systems by use of a decision matrix, which will go into more depth as we go out throughout our presentation. And these gray blocks represent the first choice based off our decision matrices. This is our design B. For the most part, these dark gray blocks represent our second choice for our decision matrix. And this is design C. Similarly, they represent, for the most part, our third decision from our decision matrix. A brief introduction before we move into the next slide. We ranked all of our systems on a scale of 0 to 4, with 0 being inadequate and 4 being excellent. You'll see S and U used in these tables. S stands for score and U stands for utility. Utility is a number that we obtain by multiplying our score by our ranking of 0 to 4, or the weight of the system. And this is our preliminary results decision matrix. We were choosing between design A, B, and C, which were outlined in the previous 3 slides. And the weights of each of these systems came from our requirements ranking that was spoken about earlier. Every requirement or system that had a total weight of 5 or up made it into this decision matrix. In keeping in mind that our power and processor have the highest weight of 13, with these criteria among others, we chose design A. These are our preliminary results, and we will speak about these systems throughout the presentation. And now Hillary Nelson will speak about the mechanical subsystem.
Thank you, Austin. The goal of the mechanical subsystem is to describe the robot's movement and structure. Topics to be discussed will be the manipulation, actuation, and connection subsystems, a finite element analysis, also the materials used for construction, and we will wrap up with the kinematic simulations. So the goal of the manipulation system is to grasp objects. Objects that we want to grasp are specified as no larger than 0.075 meters wide, and also a mass of 0.025 kilograms. The team was tasked with designing 3 different designs. The design that we had chosen is going to utilize an actuator, a servo motor, also have a solid construction type for the claw. Number of prongs will equal 2. The tips are going to be interchangeable. The claw control is going to be a direct 1-to-1 ratio from the servo to the claw. And once again, the grip type is going to be customizable. So as shown in our decision matrix here, the heaviest weighted criteria were the cost of the materials to assemble the claw, also the dexterity of the claw, and how much mass it has. So taking those heaviest weights into account, design number 2 was chosen. Keeping in mind that our first specification was to grasp an object of no larger than 0.075 meters wide, the team kept this in mind as we started designing the claw. Also, using a torque equation, we were able to find how much force was necessary to grasp an object at the end effector. So using the servo motor that is an AX12 from Dynamixel, running that at 50%, we found that the torque that we were going to be utilizing is 0.75 Newton meters. Approximately right now, our claw is 0.1 meters long. I say approximately because that is subject to change in detail. So currently, we found that our gripping force at the end is 7.5 Newton meters, which we believe to be plenty to grasp an object of 0.025 kilograms. So just as a recap, we are opening to approximately 8 centimeters. The grasping force is approximately 7.5 newtons. We're going to be utilizing a servo with a direct ratio of 1-to-1 to the gear. It has customizable tips. The reason for this is our tertiary objective is to draw in the 2017 RoboGames, and we would like the tips to be able to grasp onto a permanent marker. Also, our total mass right now is approximately 0.103 kilograms. And now Nick Harris will discuss the actuation and connection subsystems.
Thank you, Hillary. So to start off, we'll go over the actuation requirements and specifications. So for our requirements, overall we need to have 2 degrees of freedom for each joint. And for our specifications, we need to have 7 total actuators, 2 actuators per joint and 3 joints. And the base actuator at full load or full extension needs to rotate at a minimum of 12 RPM. And for the connection, it needs to be mechanically compatible with the hexapod. And it will be centered 0.15 meters from the hexapod body's rear. And the actual physical connection will be no larger than 0.1 meter by 0.1 meter. And it will be removable. So we did 3 different designs for this. And for these designs, we evaluated the actuators, the joints, so how we're actually attaching the motors to each other, the links between the joints, the robot-to-robot interlink, which is just the actual mechanical connection, and the number of degrees of freedom. And we ended up choosing design number 1 due to some of our high weights here. So the cost of the materials was tied with the amount of torque that the motors can produce, as well as the weight. And again, design number 1 was chosen. So once we chose how we were going to put everything together, this is what we actually ended up with. So our actuators are going to be servos, and each of our motors actually has 6 Newton meters of torque. So we designed a gearbox with a 2-to-1 ratio, so that base servo will end up with 12 Newton meters of torque overall. And we're using brackets for our joints, and we're using hollow circular tubing to connect our joints together. And the base of the tail will be sunk into the hexapod body. And overall, we'll have 7 actuators, 7 degrees of freedom per joint, 3 joints. So that brings it to 6. And then we're also adding the 7th actuator, which brings us to a total of 7 degrees of freedom. And we'll be using Dynamixel MX64 keys and that has a no-load rotation of 63 RPM. So here are all of our torque calculations. Some of the notable things here are at motor 2, we have our maximum torque of 4.36 Newton meters. And if you notice on motor 5, it has a 50% load on the motor to keep a smooth motion for the entire motion of the tail. We want to keep all of our motors at 50% or below. And that allows us to have a load of 0.172 kilograms. So here's our mass budget. And some notable things on here is that the motors provide a huge weight for us, and that comes to a total of 0.775. So that's the majority of the mass for the actual tail itself. And then the next largest thing is the batteries, coming to a total of 0.936 kilograms. Luckily, we can put these into the base so we don't actually have to move these around. And here is the actual physical connection between the hexapod and our tail. So the left image is both of them together, and the right image is a zoom up coming from the backside of it. And you can see that we are centered 0.15 meters from the back of the hexapod, and it is encompassing an area of 0.1 meters by 0.1 meters, and that exactly meets our specifications. And here is the simulation done in CATIA. So this demonstrates the mobility of the arm, and it can show the workspace. You'll see it come all the way around here in a second. And I will discuss the finite element analysis. So first, we analyze the bracket that's going to have the most load on it. So right here, this is going to be the lowest bracket, so it's going to have the largest load. So we applied a moment of 4.36 Newton meters. We got that number from the previous torque calculations. That was the largest moment that we're going to be seeing on this bracket. And we ended up with a deformation of 0.075 millimeters, so that's pretty small, so we're pretty happy with that. And the overall stress at the max stress points in the right-hand picture was 63 megapascals. And the yield strength for the material that we will be using is 68.9 megapascals. This is kind of all preliminary right now. We'll have to actually be testing these materials next semester to get the actual yield strength. And next, we also analyzed one of the links. You can see that circled in red there. Again, we applied the 4.36 Newton meters moment on it. And this time we achieved a deformation of 0.49 millimeters, so it's a little bit bigger. Still not too terrible for us. And at the max stress point, we got 23 megapascals. And comparing that to our yield strength of 627 megapascals, there's no need to worry about that. But we will also be doing extensive testing next semester because it is kind of a preliminary number, and we need to get actual data from the actual material that we will be using. And now Jennifer will discuss the materials.
Thank you, Nick. The material requirements and specifications state that the manufacturing and assembly of the materials must be at the available facilities on campus. The materials must also be lightweight and have a mass less than 1 kilogram, and they must be durable, so they may be reused in at least one other project. This is our material design number 2. It's a morphological chart. There are 7 options for materials and for the various points of the tail, including the gripper, linkage, and bracket. The options include the extruded ABS, carbon fiber ABS, aluminum, and 4 different types of carbon fiber. On our decision matrix, customizability and density were the most heavily weighted, and because of those, the design 2 was chosen. To recap the design 2, the gripper material was carbon fiber ABS, the bracket material was carbon fiber ABS, and the linkage material is bidirectional pre-cured carbon fiber. These do meet our specifications because they do have the ability to be fabricated and assembled here on campus. And they do have a low mass, so they should be less than 1 kilogram, and they are durable, so they should be allowed to use in one other project. And now we'll discuss the kinematics. Using Matlab, which is a mathematical computator, a code was created to find the resultant servo angles based upon a given pose. A pose is a position and orientation of an end effector. So as you can see by my hand here, as I move my hand around, I am changing its position, but not its orientation. As I rotate my wrist, the orientation changes, but not the position. The types of kinematics created were forward and inverse differential. 7 degrees of freedom does allow for 1 degree of redundancy. The degree of redundancy is nice because it does allow our end effector to reach the same position even if one of the motors does fail. One of the other problems with having a degree of redundancy is that there is infinite possibilities to reach that location now. And so to reduce the number of options and find the most optimized path, a damped Jacobian pseudo-inverse algorithm was used in our kinematics. So on the left-hand side, there is a simulation showing the dexterity of our tail. And it's similar to the CATIA simulation shown before, the main difference being the linkage length. The linkage length in the CATIA simulation is based off of our design, whereas the linkage length in this is based off of a prototype that was provided to us. And this is also very similar to the prototype, which we'll be showing a video of later on doing this similar movement. On the right-hand side of the screen, we have an additional simulation. This is to show our capabilities in the 2017 Robo Challenge, RoboGames, where we will be competing in an art challenge. And so this one will be drawing a box, as you will be seeing in a demo later on or a video demo, sorry, later on of the prototype provided to us drawing a box as well with paint. And now Austin Wild will discuss the electrical subsystem.
Thank you, Jennifer. Brief overview of what we'll be talking about in the electrical subsystem. We will start with a circuit schematic or a block diagram. We'll speak about the batteries, our actuator and processor power supply, our sensors, our processor itself, and the data transmission system. This is our circuit schematic, although it's more accurately called a block diagram. On the right, there are 4 green rectangles. Those represent our sensors as well as our transceiver. On the bottom, we have those gray blocks, which represent our 3 types of motors. In the middle, there is a blue line representative of our picobone black, which is our microcontroller. Above that, we have our red rectangles, which represent our power regulators. Above that, we have the electrical engineering symbol for a battery. And in the top right, we have another blue bar representing the Pre-Sept microcontroller, Pre-Sept being the other team building the hexapod. When we are connected to the hexapod, we will be communicating board to board, and in order to reduce errors in communication, we shall have a common ground between the 2 boards. And now Robert Noble will speak about our batteries.
Thank you, Austin. For the specifications for our power subsystem, the tail must operate for a minimum of 30 minutes. The power distribution module shall be able to supply 39.8 amps to the tail, and as a result, the battery shall have a capacity of 19.9 amp hours. Three options were considered for the battery. The most heavily weighted criteria for the battery was amp hour rating and discharge rate, and as a result, the Lumineer 21,000 milliamp hour battery was selected. However, the Aptus Era Grid 6 batteries were chosen instead. This is due to form factor. The footprint for the previously noted batteries is quite large and would be unable to fit within the given 100 millimeter by 100 millimeter area selected. These batteries are more compact and can still operate for the minimum 30 minutes. However, they cannot provide the 39.8 amps and the 19.9 amp hour rating. As seen in this diagram, the battery is connected from common ground and feeds into the motor power supply and the processor power supply. And now I will talk about the actuator power supply. For the actuator power supply, the tail distribution module shall be able to supply 14.8 volts. To accomplish this, the TDK lambda quarter brick converter was chosen. The motors operate at 12 volts and 21.6 amps. The TDK lambda can provide 21 amps and the 12 volts necessary. In this diagram, the motor power supply is connected from the battery and feeds into all the motors as indicated in gray in the diagram. So now I will talk about the power supply simulation. The 12 volt DC supply models the TDK lambda, and each motor in this diagram is simulated by a resistor in series with an inductor and a back EMF voltage. This back EMF voltage is calculated by taking the torque constant of the motor and multiplying that by the angular velocity of the motor. From this simulation, you can see that the battery that there will be a 27 amp current going through the battery, which is more than the TDK lambda can output. However, this value is not likely to be true because with very little variance in the values, there can be a very large change in the amp output. So now I will talk about the processor power supply. For the processor power supply, the specification is that the tail distribution module shall be able to supply 5 volts and 2.5 amps to the processor. These 3 design choices were considered, with cost and reliability being the most heavily weighted criteria. As a result, the off-the-shelf voltage regulator was selected. This voltage regulator, the LM2596, can take the 21 to 25 volt input from the battery and output 5 volts and up to 3 amps output. As seen in the picture, I was able to prototype the board, and since we had the components nearby to prototype it, and I was able to supply up to 12 volts to the voltage regulator. I was not able to go higher because I was using a transistor to spoof a diode, and the transistor could only take up to the 12 volts. From this circuit diagram, the processor power supply is connected from the battery to the beagle bone block as outlined in blue. The processor supply circuit was modeled here. In the top diagram, the 5 volt DC source is straight from the voltage regulator to the processor, and it feeds the BeagleBone Black, a temperature sensor, and an ultrasonic sensor. In the bottom diagram, the 3.3 volt source is one of the pinouts from the BeagleBone Black, and BeagleBone Black powers the FLIR lepton and the transceiver. As from these simulations, there's a relatively low current draw throughout the circuit as well. Now Austin will talk about sensors.
Thank you, Robert. The sensors, as was mentioned earlier, are represented by 3 of the green blocks in this block diagram. The first requirement for our sensors is that our sensor subsystem shall be able to gather information from sensing equipment. The first sensor we'll be using is a thermal camera, and we have specified that it shall be able to capture video at a rate of at least 8 frames per second. Given that our arm will be rotating at 12 RPMs, if we do some math, that means we find that the arm will be rotating at 72 degrees per second. For doing some further math, taking into account that we have 8 frames per second, that means we only need a field of view of 9 degrees per frame on our camera. The next specification for our thermal camera is that it shall have a resolution of at least 80 by 60 pixels and a color depth of 2. What a color depth of 2 means is that the camera can see 4 colors, as there is an implied 2 raised to the 2 power there. This is our thermal camera decision matrix. We're choosing between 3 different thermal cameras. The most heavily weighted criteria was that of example code, and using this criteria and others, the fluorolepton was chosen. Benefits of the fluorolepton is that it is very low price for a thermal camera. It is less than $250, where many thermal cameras on the market can cost over $1,000. There is a large availability of example code across the internet, as it is a very easy to use board or camera, and it is very easy to interface with, as there are 8 breadboard pins on this. The fluorolepton's capabilities are that it's able to capture video at a rate of 8 frames per second. It does meet the requirement of having a minimum resolution of 80 by 60 pixels, and it meets the minimum requirement of having a color depth of 2. And it also has a 50-degree field of view, which means that when we are rotating at maximum speed on our tail, we will not miss anything in our video. This is how the fluorolepton fits in our circuit. It is connected to our Beagle and Black via 8 pins. 1 for ground, 1 for power, and then several information setting pins. Our next sensor is our temperature sensor, and we have specified that shall have an operational range of 0 degrees C to 509 degrees C. We got 509 degrees C as the average temperature of a structure fire is 1100 degrees Fahrenheit, and 509 degrees C correlates to that temperature. This is the decision matrix for our temperature sensor. We're choosing between 3 different types of temperature sensors, and most heavily weighted criteria were materials and operating range. Due to this, among other criteria, the thermocouple was chosen. However, we are not using a thermocouple. We're using the Sparkfun TMP36, which is an RTD temperature sensor. An RTD measures changes in resistance to determine the temperature. It has an operating range of -4 degrees C to 125 degrees C, which does not meet our specifications. However, as this is simply a prototype or proof of concept, then we do not intend to be going into fires. We are merely proving that we can use temperature and our camera to detect fire. And it was chosen because it is very inexpensive in size. Thermocouples can get quite large, and this temperature sensor is the size of a transistor. So given our space constraints, this works out very well for us. This is how our temperature sensor relates to our overall circuit. It is connected to our Beagle and Black through 3 pins, 1 power, 1 ground pin, and then an analog to digital pin. Next is our end-effector sensor. We have specified that our end-effector shall work between 0.020 meters, or 20 centimeters, and 1 meter, and transmit its data to the microprocessor. This is our decision matrix for the end-effector sensor. Note that there are only 2 options here rather than 3, as there are not many distance sensors other than ultrasonic and IR that are reasonably priced and that the team is familiar with. Most heavily weighted criteria in this decision matrix were the operating range and whether or not it works on fire. And given that IR sensors are unreliable in fires, we have chosen the ultrasonic sensor. More specifically, we chose the HC SRO4 sensor. It's very low cost and has an operational range of 0.020 meters and up to 4 meters, which actually exceeds our specifications. This is how our ultrasonic sensor is connected to our board. It's connected via 4 pins, 1 power, 1 ground, a trigger pin, and an echo pin. And now Andrew Dietrich will speak about the processor.
Thank you, Austin. So the processor we've been mentioning throughout this presentation is the Beagle and Black, noted in the middle, circled in red. And so the requirements and specifications that best tie to our selection of a processor is that we want a processor that's capable of managing information and controlling the tail. So this means that we want to specify that the processor should have a minimum operational speed of 1 gigahertz. We want to be able to do the calculations required to operate this tail quickly, and so 1 gigahertz processor will help us with that. At a minimum of 1 gigahertz processor will help us with that. And also, we want the processor to be able to exchange data with a thermal camera, the temperature sensor, the ultrasonic sensor, and a minimum of 8 actuators. We want to ensure that all the data flow is going through the Beagle and Black itself. And also, we want the processor to use no more than 3.7 watts of power, as we want most of the energy supplied from our battery to be used by the actuators themselves. So looking at the decision matrix for our processor, 3 options were considered. The heaviest weighted criteria were the processor speed and the available documentation, as it is very difficult to use a board with little to no documentation. And with these criteria in mind, among others, the BeagleBone Black was selected. And so on board, the BeagleBone Black has a Cetera 1 GHz processor, which perfectly meets our first specification. And we have 65 GPIO pins, 8 PWMs, 4 timers, 4 UARTs, 2 I2C, and 2 SPI ports. And so all this boils down to is that there are many ways to communicate for the BeagleBone Black to communicate to off-board peripherals. Also, per the spec sheet, the BeagleBone Black at max draw will draw 460 milliamps of current. So given the 5-volt supply that is given, at maximum, working its hardest, it will only draw 2.3 watts of power, which is much lower than 3.7 watts we specified. And now Robert Noble will discuss the data transmission.
Thank you, Andrew. For our data transmission specification, the transceiver must be capable of transmitting to a distance of 100 meters away at a data rate of 20 kilobytes per second. This number was calculated by taking the rate of data that the camera would be giving images to the processor and adding an additional 1.25 kilobytes per second for overhead, resulting in a 20 kilobyte per second value. These 4 options were considered for the transceiver, with cost and data rate being the most heavily weighted. As a result, the SparkFun NRF24L01 was selected. This transceiver can receive and transmit at 31.25 kilobytes per second at the specified distance of 100 meters away and is relatively inexpensive. In the schematic, the transceiver is connected straight to the BeagleBone Black. Simply enough. And now Hillary will talk about the software subsystem.
Thank you, Robert. Within the software subsystem, we will go through a kinematic flowchart, an autonomous operations flowchart, and finish with the programming language chosen. In order for our robot to move, we had to derive a kinematic controller. This semester, we made a kinematic controller. After initialization of the program, we enter into the program to check to see if the pose is within the robot's workspace. If it is not, we prompt the program to start over again to find a workspace that's within the robot's reach. After we find that the pose is within the workspace, we set up our configuration vector, which is a vector of joint angles. Next, we calculate the forward kinematics, which enables us to find the joint velocities. After that, we find if our error position and error orientation is reached its end point. What the error means is if the robot is within a certain threshold of finishing its task to be at hand. If it's not there yet, we continue on, and we calculate then using the damped Jacobian pseudo-inverse algorithm in order to find the joint velocities that are needed. We update our vector and the process continues over again. Once we have reached our final destination and the robot has come to its final destination, then we execute the movement and we end the program. Next, Andrew will talk about the autonomous operation.
Thank you, Hillary. So in regards to our tail system's operation in autonomous mode, we first start out by checking our servos, our sensors, and our transceivers. This is done to ensure that all of these components are working properly and outputting correct data. If any of these checks should fail, so for example, if our transceiver is not outputting correct data, then we will not even enter our autonomous operation, as those problems need to be fixed before possible damage is done to the tail. So once those have been completed, we enter our main autonomous operation while loop, which is notified the circle with the X. So we start out with our main mission. We're scanning for fire. So the tail will move in order to scan the workspace for fire using the FLIR lepton. And also we will, if a fire has been identified, the user, the remote operator, in this case a user, would be alerted of the fire. Then we will conduct a sensor pull and a battery pull. These are done to ensure that the tail is operating safely. For example, we're pulling the ultrasonic sensor to ensure that our end effector is not bumping against an object, possibly causing damage. And the battery pull is done to ensure that there isn't sudden loss of power during operation. We don't want to drain our batteries completely to zero, as at that point the tail would untorque and could possibly hit the ground or an object and cause damage. Once those have been completed, we will then calculate our center of mass and position, as when both the tail and the hexapod are joined together. This is very important information to ensure smooth operation once both systems have been integrated into one. So this information is then transmitted to the hexapod itself to help assist with their movement. This process is repeated until either a user-generated termination signal has been given or the end of mission has been reached. And now to preface the prototypes that are to come, we used a RoboPlus software suite and a Robotis CM530 microcontroller. This microcontroller is not robust enough or does not have the processing speed capable of calculating the inverse kinematics on the fly. So all of that work was offloaded to Matlab. Matlab was used to get the servo encoder angles, which was then supplied to this microcontroller to produce the prototypes you'll see. And this is very limited. This microcontroller is limited as only 7 instructions can be executed in one operation block. So this is a more high-level LEGO Mindstorms microcontroller, is what it boils down to. Using a BeagleBone Black, however, we will be able to ensure that there are enough steps required to create an autonomous system. So we do not have this limitation. So in this demonstration, as Jennifer mentioned earlier in Matlab, this is showing, in a Matlab simulation, this is showing the dexterity of our robot and its where it can reach its range of operation. This prototype was constructed by Dr. Gentilini. Our actual design is not as limited as this, as the brackets on this may reduce its dexterity. Ours will have a much wider field of range. Excuse me. And then in this demonstration, we will be painting a rectangle, as Jennifer mentioned earlier. So in this simulation, note that this microcontroller and the servos themselves are not super robust. So that's where that initial dot comes from, as we're not able to, the control system isn't robust enough to account for that. As this is drawing the rectangle, you'll see that it is darker in some areas and lighter in others. This is because using this microcontroller, the system is not robust enough to change given a very distance between the paintbrush and the piece of paper. And as you saw on the bottom right of the rectangle, it didn't look like a rectangle, it was curved, as the paintbrush bristles were not at the correct position to draw a straight line. And again, this is due to the microcontroller not being robust enough to do this. But this is an outstanding proof of concept for what our more robust system using a BeagleBone Black will be able to accomplish. And so now I'll go into the programming language selected for this project. So the requirements and specifications that best link to our decision of what programming language to use are in regards to the data acquisition. So the data acquisition subsystem shall be able to interpret the received data from the environment, from the sensing equipment, in order to create an autonomous system that can operate safely. So to specify this, we'll be able to process data from a thermal camera once every 125 milliseconds, from a temperature sensor once per second, and from an ultrasonic sensor every 20 milliseconds. And so 3 options were considered for our programming language: ANSI standard C, C++, and Python. The most heavily weighted criteria were familiarity to the available libraries. And so with this in mind, the C was selected using this decision matrix. However, C++ and Python are more widely used in the robotics industry, and we wanted to ensure that all members are getting the proper experience required to enter into that industry, so C++ will instead be used. And it also has a vast wealth of libraries that support creating an autonomous system. Many libraries exist for communicating with a variety of sensors and actuators. And this comes at no cost to the team, as the compilers and environments for these programming languages exist on campus. And now Austin Weil will discuss the budget.
Thank you, Andrew. So this is our itemized budget for our system. There are 2 columns for price, one market price and one team cost. Market price represents the price of our components without any discounts or student discounts or availability of parts on campus. And the team cost on the right represents discounts or parts already being on campus, taking into account the cost reduction that would come as a part of that. Our budget overall is our grand total is $2,059, and the most expensive part of our system are our motors, coming in at more than $1,500. So far, we're actually $1,000 under budget, so we have much leeway in the future. I'll now speak about our future timeline. This is very small, but I'll highlight some stuff for you. We intend to start a week before the construction of our robot, 1 week before the semester begins, where we will print out some inexpensive plastic parts in order to verify the design of our brackets. And then in the next 2 weeks after school starts, we intend to build the robot in its entirety so we can dedicate the rest of the semester to programming and coding this thing. The most time-consuming part of our programming will be development of the drawing capabilities of the robot, which is dictated by that very large line at the bottom of your screen. And even though drawing in the RoboGames competition is only our tertiary objective, it is one of the reasons why we have as much funding as we do. So we want to do our best in order to meet that goal. In conclusion, this is our design. We spoke about each one of these. Some notes on this: our battery, temperature sensor, and programming language are different than what we decided in our decision matrix, and those reasons were spoken about earlier. The specifications we did not meet were that of our power distribution being able to supply 39.8 amps, the battery being able to have a capacity of 19.9 amp hours, and our temperature sensor having a range of 0 degrees C to 509 degrees C. We would like to thank Dr. Gentilini, Professor Mangum, Professor Helbling, Professor Kodemer, Dr. Davis for their help, the College of Engineering and the Undergraduate Research Institute for their funding, and our panelists. Thank you for coming. Are there any questions? Yes,
I got a
Dr.
question for Robert. You talked about your batteries that you selected. You said what they were, but what type are they? Lithium-ion, polymer?
I believe they are lithium-ion. Yeah, lithium-ion batteries.
Okay, and it says you're putting them in parallel.
Yes.
How are you hooking them up in parallel to make sure you don't end up with a slight difference in voltage between the batteries that's going to cause a current surge when hooking it up? You have any sort of safety features on there?
I did not consider that when selecting the batteries, I'm sorry.
Okay, so you might want to talk to Professor Kodemer. I know he's worked with some other teams on that, but especially with the lithium ones, they can be unstable if you put them in the wrong conditions. Second thing, you talked about the power regulation. What kind of regulator is that?
For which?
LM2596 that you selected, is that a linear regulator?
That is a buck converter.
Buck converter, okay. And you listed voltages. Did you look at power consumption and how much would be absorbed by that?
From the power consumption of, can you please specify?
Yeah, I guess my question is, are you going to have to heat sink that for power dissipation? Because you're dropping 15 volts at 3 amps.
I did not notice a problem when I ran it to 12 volts, but I did not consider the power that would be consumed by the buck converter itself.
I can speak more on this. In this photo, you can see of the part itself, there are pins in the front, and in the back is actually an area to attach a heatsink to. So they designed it to be able to be compatible with the heatsink.
Okay, and have you done any calculations to determine whether you need that heatsink or not? And
Not yet.
so forth? Okay, so something to consider, because it's going to be absorbing some energy that you might need a heatsink.
So I have a few questions. So the first comment was pictures. So I heard the word hexapod, and then on slide 30 I saw something that looked like it might be a hexapod. And just pictures in general, and once again, I think I said this in the other talk as well, but if you're kind of walking through a design piece by pieces, put up a picture and say, now we're designing this part, now we're designing this part, just for some reference.
Okay, thank you.
Slide 34. this is your finite element, and it looks like you're well within any requirements. But I was just going to ask, so it looks like that's a static based on the payload and the moment arm. Is that how you determine the applied moment and the applied loads?
The moment was based off of the torque in our torque calculations. That's just the maximum torque that we're going to achieve when we're holding our maximum load. And so for this ANSYS simulation here, the bottom part of the bracket was held static, and then the moment was applied.
Okay. Yeah, so just be aware, I think you're well within any kind of range, but when things are moving, sometimes the load's a little bit higher than the static analysis. I had a question about the thermal camera. What exactly is its purpose? Is it detecting a fire, or is it determining the location of the end?
So your question is, what is the purpose of it?
What's the purpose of the thermal camera?
As per our primary objective, we want to detect fire and communicate that information. So the purpose is it will be part of our fire detection system.
Okay. And then, so the follow-up then is to determine like the location, the XYZ of your actual claw or point. How are you doing that?
The way in which we'll do that, the motors that each have encoders go to them in a microprocessor, and we will determine the location of our arm based off those encoder steps.
Okay. I heard the phrase Dan Jacobian pseudo-inverse a few times. Is that something that y'all are doing, or is that a Matlab tool that's being used? Or?
It's a kinematic controller that we derived in order to make the movements.
Okay, so it's something that you put together?
Yes.
Okay, and then the follow-up that I think you've answered is, can you get that into C++? And if you did it yourself, it sounds like you can. And then there was one, I think slide 105, where you had a decision matrix and you went with something else.
Correct.
I just put out that it seems like there's something wrong with your decision matrix. It's that, your weights, if familiarity is what you care about the most, then the weight should be higher.
Well, one of the reasons why we decided to go with C++, despite our decision matrix saying otherwise, is as we are at a school, we are interested in making it more of a learning experience rather than an easy experience. And that is one of the biggest criteria that went into choosing C++, as the robotics students will be using it in the future, and they might as well learn it when they're at school.
Okay.
Does that answer your question?
Yeah, that's great. Thank you. It was a great presentation.
Thank you, sir.
Thank you.
If you want to go to slide 48, I appreciate that you mentioned a couple of times that these are not actually schematics, despite being titled as schematics. Why is it critical that you actually present schematics in an environment like this?
Well, as you said, they're not entirely schematics, but one reason for doing it was so just to give everyone an idea of what we are talking about, a more pictorial representation of what we're speaking of.
Well, why we want to see a schematic in an environment like this is so that we can tell you if what you're doing is going to work. Okay? What you have here, there's no way for me to know if it will function without significant additional information. So let's talk about significant additional information right now. Okay. Just one example here, the temperature sensor that you have on this block diagram. What are those three wires going to be?
I don't think I understand your question. What are they connected to?
What are they connected to at the blue BeagleBone black bus?
They'll be connected to the, if I remember correctly, the 5-volt power pin, the ground on it, and then the analog to digital converter pin.
Okay, it's interesting that you mentioned analog to digital converter, because when you talk about the BeagleBone black, that's one subsystem that you don't even mention on the BeagleBone black. But it is present there. If you use a 5-volt and a ground and an analog, which makes sense, will you need any additional components for that to function?
According to what I've seen on the spec sheet, I do not believe so.
Then you believe incorrectly. You will need many additional components for that to function. And so that's why we want to see a schematic.
Okay.
Because we'd like to be able to tell you if something is going to work. I can tell you right now, if you don't have any additional components, that temperature sensor is not going to work, nor will, as you know, the regulator for the 5-volt supply. Right? You'll require numerous additional components there. Why we want to see that is so that we can advise you if it's going to work or not, the way you presented it. The other thing is those components are not currently on your costing. Right? You're going to need a number of additional components for the power regulator for the Beagle and Black. You're going to need some additional components for the temperature sensor. I believe you're going to need some additional components for each of your three additional green blocks there. So at the moment, we cannot give you advice on whether it's going to function or not, because you haven't given us a complete schematic.
Okay.
So you've given us a theory, but not any ability to do a design review.
Okay.
Does that make sense?
Yes.
Okay.
One other comment on that one, you've got power and ground that are tied to the Beagle Bone Black. And my concern is always people sometimes try to treat their microcontroller as a power supply, which it's not. Okay, I'm assuming you have some sort of regulation in the Beagle Bone Black that you can grab off of. Is that where you're getting your power?
For
the
our
Beagle Bone Black
sensors.
is a board, right? Not a chip.
Right. Yeah, it's a board. It's a
And so it actually
microcontroller.
has a power regulator on there.
Yeah, it is a
Okay,
microcontroller.
that was just my concern.
And that gets back to, if you go to slide 64, okay, what Professor Skipper's talking about is, will you be able to supply that 60.73 milliamps from the onboard power regulator?
We have not verified that.
And I have Beagle Bone Blacks with blown power regulators, which would suggest no. So once again, you're going to need additional components to be able to handle that 3.3 volt load, which are not represented in your block diagrams, which are not represented in your bill of materials.
Okay.
Okay. That's the extent of my comments, but there's a lot of systems here that you haven't presented adequate detail for us to be able to see right now, will they function? Conceptually, yes, but there's a lot of details, for example, with the temperature sensor, that I don't think you've considered based on the level of schematics we've observed.
Thank you for your feedback, Dr. Davis. Are there any other questions? Yes, Dr. Benavides.
I just have a couple of comments. Always be careful with your claims. All right, so for example, if you go to slide 34, you have a deformation of 0.075 millimeters, and you mentioned during the presentation this is acceptable. Based on what? Is there a requirement associated with deformation? Is there a requirement that has been established based on, basically what I wrote down here is how much, on slide 34, how much deformation is acceptable until you start seeing a deviation from the motion that you're expecting. Is there a requirement for that? There has to be. If you're going to make a claim, this is acceptable, this is not acceptable.
Okay.
All right, same thing with slide 36. Deformation, you make the same claim. Okay, there should be a requirement associated with that. Slide 43. Forward kinematics, can you define that as opposed to inverse differential kinematics?
Jennifer? You want to speak to this?
Speak to it if you would. Forward kinematics, to answer your question, forward kinematics are what are used in order to find the joint velocities at the time. Then the inverse differential kinematics is more ties into what we were talking about before with the damp Jacobian pseudo-inverse, and that's helping finding our. If you want to put that slide up, and that helps find our more of our velocities taken. So one is our position. I'm sorry, I misspoke before. One finds our position, the other finds our velocity.
It'd be good to define those. Not everybody knows the difference.
Yeah.
So, okay, slide 45. How was that animation made?
Using the forward and the pseudo matrix as well. The slide that was just up, using that algorithm, we did several scripts and functions in Matlab, and we were able to derive the motion of the robot.
So was that a for loop? I mean, did you calculate the motion before and then you animated the motion? Or?
This is, we know the lengths of in robotics, we make a DH table, which gives the links of where each of the actuators are connected. And from there, taking that information, this is exactly the prototype that Dr. Gentilini has made. And modeling after that and knowing that the limitations of how it can turn, the restrictions that the robot can make and make within the workspace, we're able to put that into Matlab code and derive the actual robot that you see.
One thing you can also do in the future is you can also draw your mechanism on Matlab.
Yes.
And animate that using HD transform functions that are built in Matlab. Okay, great. 102, please. All right, just really tricky question. Why did you select the brush as opposed to some other writing apparatus?
Not dangerous.
So I believe I mentioned, but in the case of this microcontroller that we used, it was not robust enough. So for example, we started out with a pen or a pencil. So given the varying distances between the writing utensil and the canvas itself, it would drift away or it'd start to push into the object, and the microcontroller and then these servos as well was not able to account for that, as we couldn't make a system robust enough using that microcontroller. So given a hard-tipped writing utensil, it would stop, jitter around, and it wouldn't actually complete the drawing. So a brush with the long tip was used so that there's a little bit more give throughout the drawing process. So in the beginning, it's very dark because it's pressing very hard, but as it moves along, it can't adjust for that, and maybe go in a little bit closer or drift out. And so that's why, and then at the end, the brush is deflected, which means that our rectangle wasn't able to exactly represent a rectangle. But using the BeagleBone Black, it'll be much more dynamic. We'll be able to adjust to the distance and create better drawings. If that answers your question.
Yes, thank you. One last one. 113, please. I don't know if this was mentioned, I was writing the notes, but what do you expect, what do you intend to do about these specifications that have not been met here?
We do not intend to do anything about it.
How does that affect the goals of your overall project?
Rubber kits.
Yes. On further calculations, it takes a lower current to power the tail system. So the requirements can still be met, but yet not the specifications.
For example, the specification 2.1.3, a 19.9 amp hour battery, those are very large and can be quite expensive in order to reduce costs in both money and size, even with a lower amp hour rating battery. And what that affects is that affects our battery life. And we had calculated for a 30-minute battery life, but given both, we will be fine operating off 15 minutes or more that we have provided our batteries now.
That's all. Thank you. Great presentation.
Thank you very much.
Thank you. Are there any other questions? From the audience, perhaps?
I have one question.
Yes, sir.
The entire system, the goal of the system is to measure temperature. The apparatus itself, what is the heat tolerance of the entire system? Have you tested it?
We do not have our components and we have not tested it yet, but we do not intend to have this be going into fires, as if we were to build all of our components to be able to survive within a 1100 degree Fahrenheit room, it would significantly drive up the cost. And even though we are under budget now, we would not be able to, we would not have a big enough budget in order to pay for that amount. Does that answer your question?
It does.
Okay.
So you need more funding.
Always.